reactions. These reactions are nucleophilic, right? So they're substitution nucleophilic and second order. They follow second order kinetics, which means that the rate law is basically K times the concentration of the alkyl halide and the nucleophile. Now these reactions are concerted, which means that it all happens in one step, right? All bond making and all bond breaking all happens all at once. Now Sn2 typically favors strong nucleophiles. So what does that mean? Something that's negatively charged. So OH minus, SH minus, Cn minus. These are more the common nucleophilic things you're going to see when it comes on to Sn2 reactions. Now they also favor polar aprotic solvent, which means that the solvent doesn't have any hydrogen bonding at all. So some perfect solvents are DMSO, right? Acetonitrile, acetone, DMF, and we all know acetone looks something like this. Notice there's no hydrogen bonded, so that's what we mean by polar aprotic solvent. Important to remember, these show inversion of stereochemistry, and we will visit that a little bit later and what that means. These favor primary alkyl halide, which means that most of the times when you have a primary alkyl halide with two hydrogens, that is so open for attack that a negatively charged stuff is ready to go, and so that will almost always happen in one step, right? So with that being said, let's look at some reactions. So what if I have this compound here and decide to react it with sodium cyanide in DMSO, right? What will be the products? Well, again, we could cancel our sodium. This will be your nucleophile, this cyanide thingy right here, right? Now notice our solvent is polar aprotic. Now we have a secondary alkyl halide here with the presence, right? We have one hydrogen here, so we have a secondary alkyl halide here. But this does not care because, again, it is very ready to give up its electrons, right? Because the cyanide anion looks something like this. It's ready to donate this pair of electrons. So what's going to happen? These two electrons of the cyanide is going to come in, attack the carbon, expel the bromine, and notice everything happens in one step. And now we get something that looks like this. All right, and this will be our product. How about another one? How about this? What if we had methyl iodide? Right, and we add this in some OH minus, and maybe we would add DMF, polar aprotic solvent. Well, notice again, we have in this case, we have a methyl alkyl halide, and this is very open. You could imagine this carbon has 3 hydrogens. This is very open to a negatively charged hydroxide anion, right? So again, comes in, well, sure they are in the wrong place, but it pretty much comes in, attack the carbon, expel the iodide, and we have something that looks like this. All right, we form methanol. Right? How about another one? How about we have a C and an H here, we have a bromine here, and we have a CH2, CH3, and a CH3 going away. Right, and we add some Cn minus. Right, what is going to happen? Well, again, remember, when we talk about stereochemistry with Sn2 reactions, well, we have a secondary alkyl halide here with just one hydrogen, but because this is negatively charged, it does not care, right? So this is going to readily open attack. So here's what it's going to do. It's going to attack from the backside, attack the carbon. This bromine is going to be expelled. Now the intermediate looks something like this. Right, the intermediate looks something like this. Looks as if like, all right, we have a CH3H here. We have a CH2, CH3. Intermediate looks something like this. Right, so you can imagine this cyanide is kind of attacking the carbon while this bromine is leaving, and that's what the intermediate looks like this. But in terms of the product, this shows inversion of stereochemistry, which means that I have my carbon here, My C2CH3 will stay here. Yes. Now my nucleophile will be substituted, and maybe this should be a CN. So my CN will be attached here, right? My hydrogen will still be there, and now my CH3 will be in front, right? So this will be my product, right? This will be my product, right? Notice how from the reactant side, my bromine was in front, but my nucleophile that has been attached to the carbon is now behind. And what that does is show inversion of stereochemistry. And what that simply means is that, okay, well, let's label priority groups. Well, my bromine will be number 1. It's obvious to see that this will automatically win out from this methyl group here. So this will be 2 and this will be 3, right? So this is going 1, 2, 3. It's going right, but because our priority group is not away from us, this is really S. Right, so this is going to R, but the priority group is not away from us. We haven't done any flippings. This is S. Over here, look what happens, right? We have a CN. Well, the C's are both equal, but if we go one out, you can hopefully see that we hit a nitrogen. So this will be priority group number 1. This doesn't change. Priority group number 2, priority group number 3. Right? Now look what happens. I'm going from 1 to 2 to 3. And I'm going from 1 to 2 to 3. Right? So I'm going left, right? I'm going S, but because my priority group is not going away from me, I'm going to take the reciprocal of that, and I'm going to R. So notice we went from S to R, and that is what we mean by inversion of stereochemistry. How about another example? What if we have this molecule here? All right, and we react this with OH minus, right? What is going to happen? Well, again, you could see that this is a primary alkyl halide with 2 hydrogens here. Maybe we should draw in our hydrogens so you could see, right? We have a primary alkyl halide ready for attack with a negatively charged hydroxyl anion, right? So this is very nucleophilic, so it's going to come attack the carbon, one step expel the bromine, and we get something that looks like this. All right, how about this one? Right, what if we react this in acetonitrile? All right, polyprotic solvent, very strong nucleophile on a secondary alkyl halide, but that does not matter. The nucleophile is very strong. What will happen? Well, again, these electrons are going to come, attack the carbon, expel the bromine, and we get something that looks like this. And this will be a product. This is what we mean by inversion of stereochemistry. This is exactly what we mean by inversion of stereochemistry. Notice that my bromine, my leaving group went from a dash to the nucleophile being a wedge, right? So that's what we mean by stereochemistry. And what this does is change the R and S configuration.